Stripping down science. The Naked Scientists.
How much do people actually get through to their dog when they say something to them? What does the dog take away from the conversation? And what would happen if a person were exposed to the vacuum of space without a spacesuit? Would they go bang? Well, we'll find out shortly, because it is our Naked Scientist Q&A show this week. Hello, I'm Chris Smith. It's Sunday, August the 12th, and with us this week to answer your science questions is Victoria Gill and Dominic Ford.
On the way, news of the discovery that Stone Age men were the first lumberjacks, and how space scientists have found some of the universe's missing matter in our own cosmic neighbourhood.
And we'll find out how to knock epilepsy on the head with a tiny but carefully timed bit of electric current.
And we have banished our kitchen science guru, Dave Ansell, to the kitchen. What are you doing there, Dave?
Well, I'll be here playing with electrochemistry. I'm trying to find out if I can make a battery to charge a mobile phone using just some fruit and a few nails.
Sounds electrifying. Thanks, Dave. That's all on the way.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And straight out of the blocks, Mike Hammond is on the phone. Hello, Mike.
Hi, good morning, Chris.
OK, what can we do for you?
Well, I've got a 14-month-old cat. When I give him a belly rub, he keeps opening and closing his front paws. And I want to find out why this is.
What's the cat's name?
Teddy.
OK. Vic, what do you think? What does a cat take away from a conversation with a human? And what is all this belly rubbing action? Sounds like me in the morning when I get my belly rub.
I don't want to know about your morning habits, Chris. Well, it sounds like Teddy's a very, very contented cat, because lying on its back like that is a very submissive posture, which just means it very much trusts you, Mike, and really wants to sort of be around you. You're head of the pecking order. But what that opening and closing of paws is about is actually that's a feeding kind of stimulation. So when cats are kittens and they're suckling from their mothers, they actually paw at their mother's teats to try and stimulate lactation. That movement actually stimulates the milk flow. So that's what your cat is doing there. It's a reflex action, and it's also a sign of complete contentment. So I think you have a very happy cat.
Oh, he waits for me and runs in the living room when I get up and lays down waiting for me.
Do you remember, Vic, and also, Mike, this is relevant to yourself, there was a story a few years ago by a lady at the University of Sussex. Her name was Karen McComb, and she was working on something totally unrelated to this, and she kept getting woken up in the middle of the night by her cat. And it used to come and sort of scratch at the door to say, I want some attention, or let me out, or whatever. And she thought she could detect a subtle difference in the purr of the cat when it wanted something. So she actually recorded it and took it into the lab, and she recorded the cat's things into a computer, looked at the audio spectrum, and she saw that the cat's purr, running along at between 50 and 100 hertz, was punctuated by these cycles of 300 hertz. Now, that's the same frequency a baby cries at, and so she theorised that what's going on is that the cat has learned to plug into your sensitive side, mimicking a baby, so that you pay it some attention.
Amazing stuff. And it's incredible how those subtle sort of evolutionary changes have happened with domestic animals. We're finding a little bit more, hopefully later in the show, about how dogs have sort of become accustomed to deal with our own signals and even our own vocabulary as well. It's fascinating stuff.
Vic, thank you very much. Now, Dave said he was doing something interesting in the kitchen and he's going to try and power an iPod or a mobile phone with some fruit. Ben's with him. What are you guys doing?
Well, Dave has absolutely taken this kitchen over, and it now looks like a strange mix between an electrician's workshop and a greengrocer's, because he's got piles and piles of fruit, and he's got those things called digital multimeters that you can use 2 bits of wire and it'll tell you voltage and current and that sort of thing, and loads of nails. Dave, what are we actually doing?
What we're going to try and do is build a battery. You may have heard of a fruit-powered clock or something like that, so we're going to try and build one of these. Now, to do that, you need 2 different metals and some fruit. So, to start off with, I've got a galvanised nail, which is covered with zinc, which is a fairly reactive metal, and I've got a 1p piece, which is a nice piece of copper. And then what I've done, I've wired up both of these to a multimeter, which tells me the voltage which is being produced by each one. So I can then push the nail into the fruit, and the 1p piece in quite close to it, maybe 5 or 6 millimetres away.
So they've both gone into a nice ripe-looking apple, which seems a bit of a waste of fruit. But already we're actually seeing a readout on the multimeter. So just putting two different metals in a bit of fruit has given you some electricity.
Yeah, that's right. Essentially what's going on here is a chemical reaction. The copper is covered with copper oxide, and the zinc is much more reactive than the copper. So what it wants to do is grab the oxygen from the copper oxide and form a chemical reaction. But to do that, it's got to push electricity around the circuit, and so you get a voltage. Now, this is producing about 0.9 volts. My phone will charge from a USB socket, which uses 5 volts. So I thought maybe I would try in the next few minutes wiring up 5 or 6 of these and see whether we can get enough voltage to power my phone.
Dave, is this safe?
I wouldn't recommend you did it with anybody else's phone, but this one's near the end of its contract, so we'll see what happens.
And hopefully it shouldn't be too much electricity to really be dangerous. So I think we're going to keep going. We've got a big bag of apples. We're going to do as many of these circuits as we can. And if you could come back to us later on, we'll see if we've actually got it charging. Food
for thought. Thank you both very much. OK, Mark's on the line. Hello, Mark.
Hello.
OK, fire away.
A question regarding black holes. Since I know that black holes can lose mass through Hawking radiation, and the force of gravity is related to the mass, is it possible for a black hole to lose sufficient mass that it no longer is a black hole and has moved up the scale to do something like a neutron star?
Sounds like one for Dominic. Dominic, first of all, tell us what actually is Hawking radiation?
Now, there is a process by which black holes can lose mass, and what happens is that all the time in the vacuum of space, there's a quantum process by which particles and antiparticles are popping out of the vacuum of space. Now, if one of those two particles, the antiparticle, falls into the black hole, and the other particle, the real mass particle, does not fall into the black hole, then you've got a particle out of the black hole. The antiparticle has fallen in and will annihilate with the matter inside the black hole, and that causes the black hole to lose mass. Now, this is a very slow process for the kind of astrophysical black holes you see in the centres of galaxies and that form out of supernova explosions. But if you were, for example, to take a small black hole, I did a calculation a while back for one the size of a double-decker bus, then this is actually quite a fast process, and a black hole the size of a double-decker bus would last about 1/1000th of a second before it would just evaporate into the vacuum of space. But obviously, real black holes are around about the mass of the sun, or many millions times that mass, and they will lose mass very slowly compared to the amount of mass they have.
Otherworldly stuff there. A little bit closer to home, Ralph in Stamford would like to know why some thunderstorms have lightning and some don't.
I think that actually, if you are going to have a thunderstorm, that means by definition you're hearing thunder. So if you're hearing thunder, you're hearing a shockwave. And what's happened during a thunderstorm to make that shockwave is that something has heated a patch of the air to a very high temperature, and it's made the air expand supersonically, making a shockwave, and that's then coming towards you through the air as a rippling roll of thunder. So you can't really have the heating of the air without some kind of electrical discharge, which is what the lightning is. And in fact, I think when people have done calculations and measurements, a lightning bolt actually registers a temperature of about 30,000 degrees C, which is 5 or 6 times hotter than the surface of the sun. So I don't think you can have a thunderstorm without a lightning bolt, because you wouldn't hear any thunder, because some discharge has got to actually drive that happening in the first place. So I think probably it's just that the lightning is masked behind a layer of cloud or something and you just don't see it. This one's quite interesting, Vic. We've talked about cats so far. Now, Anthea Sam says, how much do dogs understand of humans when you talk to them? There's that famous episode of The Simpsons, isn't there, where the dog in The Simpsons, what's the dog called? I can't remember. What's the dog called in The Simpsons? Somebody.
That's my appalling lack of modern cultural knowledge there.
Ben has just pointed out Santa's Little Helper is the name of the dog, but that they do this wonderful sketch where Homer is berating the dog for something, and the dog is sort of looking at him, and all the dog hears is blah, 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 biscuits and blah, 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 food. So what's the bottom line on this?
Well, it seems to be that there's actually been a number put on the number of words that a dog can understand, of sort of in the human lexicon, I guess, and that's approximately 200. That was a dog called Rico, which sadly passed away in 2008, but it was a dog that was studied studied at the Max Planck Institute for Evolutionary Anthropology in Leipzig, and they do a lot of work on this stuff, sort of understanding how dogs have adapted to sort of human culture and language. But that seems to be the maximum, and it does really, really vary according to breed. Rico was a Border Collie, and that's a working dog that's really been trained for its ability to be able to understand and work with a man to sort of obviously to sort of run sheep and respond to those commands. So that's something that's been bred into that line. And when you have dogs, breeds that are maybe bred for their appearance more so, they might be suffering a little bit on the intellect there.
Oh dear. Certainly, my mum had a dog. Unfortunately, he has now died as well, but he had an exceptional vocabulary. And the other thing that they were saying dogs seem to be able to do is, I mean, the experiments with Rico that you were saying there, they would have him in a room and say, go and get a toy of type X from the room next door, and then not include that toy in a lineup of toys that he did know the name for. And he would assume that because he didn't know what that toy was named, and he had been told to go and get things that he didn't have the name for, that must be the one. And that's the same sort of learning process that 3-year-old kid shows. It's quite extraordinary that they're able to do this. But then on the other hand, given that they are mammals and so are we, and we have common ancestors, is it so surprising?
It is extraordinary. I think it does show a level of sort of adaptation and how quickly it's been bred into dogs, well, into their breeding lines, that they can kind of cope with this sort of communication with humans. The other thing that they've shown in these kinds of tests is that there seems to be a real connection with the dog, between the dog and their owner. So the specific human that the dog's associated with, that they're more likely to understand, follow the commands, and even respond to their facial expressions if they're the dog's owner and they recognise that person.
And equally, owners respond to the dog's expressions as well, don't they?
Quite.
Vic, thank you. Dominic, Ahmed Youssef has written in and said, what happens if you are exposed to the vacuum of space? Would the person explode due to a lack of air pressure, or would they freeze first because of a lack of heat?
That's an interesting one, because if you read books, what the books will often tell you is that the person will explode in the vacuum of space. And I've been thinking about this for a little while, and I'm not actually sure I quite believe that, because something you will often hear in the news is that aircraft have depressurised at altitude. There was a case over Australia a few years ago where a plane developed a hole when it was flying at about 40,000 feet. And the pressure up there is only about 20% of the pressure on the surface of the Earth. So that's about 80% of going to the vacuum of space. And everyone on that aircraft survived. People routinely survive aircraft depressurizations. It's quite unpleasant, but you don't explode. So my guess would be that you will pass out quite quickly unless you have a source of oxygen. The air will obviously be sucked out of your lungs, and oxygen from your bloodstream will start to leach out into your lungs. You'll get something very similar to bends, like divers get, and it will all be very unpleasant. But as long as you are quickly restored to pressure, I think you might survive.
Can I ask you a follow-on then that's also been sent in? Aman Sharma has emailed chris@thenakedscientist.com and said, will ice melt in a cold, dark vacuum? Because you're saying that your sort of body fluids exposed to a very low pressure will boil and therefore you will lose them as gas. So if I had some ice in space, what happens to that? Does that boil off as well?
Yes, boil isn't actually quite the right word, because boiling is going from a liquid state to a gaseous state. In fact, at the very low temperatures in the dark coldness of space, there is no liquid state. You go straight from solid ice to vapour. So the word is sublime for going from a solid to a gas. But ice particles will tend to sublime into the gaseous state, yes.
Okie dokie, Vic.
Well, we've been looking across what's been in the news headlines this week as well, and I've picked up something that is really, really interesting in the journal PLOS ONE. This is a very clever team at the University of Tel Aviv who've been looking at a site where early Stone Age man lived in a community there, and they found some tools that show that early Stone Age man was actually the first lumberjack. Now, we know that there was a real revolution in the way humans lived during the early Stone Age, that they started to farm and sort of build more permanent settlements, but these guys have really, really pinned it down. The early Stone Age, about 8,600 BC, they found these axes that are able to actually chop down trees. And they've actually looked at these flint tools, these axe heads, to show how the wear and tear to these heads and how strong and powerful they are, to show that, in fact, yes, these men, they did actually begin to chop down trees, clear land, and then use that wood as a building material. So we have a pinpoint date on when man became the first lumberjack and where we started to really use wood as a material to kind of improve our lives and build more permanent settlements.
Do they give any speculation as to what triggered them to want to do that? Why they weren't doing that and then suddenly they did want to do that? Was it just that someone realised wood's a convenient building material?
Well, it seems like they were already using flint tools in kind of very modest carpentry. So there were small flint tools to sort of work away at wood and use it maybe in kind of cooking preparation, use it to build some sort of rudimentary additional tools and axe handles and things like that. But I think at that point there was just this revolution, really, where they looked around them and they saw that there was this huge resource of wood, and if they had tools that were strong and heavy and powerful enough to be able to use that as a resource, not only could they take that down and have huge structural material, but they could also clear all of that forested land and use it for farming.
And why didn't we spot this before?
Well, it's all about the preservation and these particular sites that are so beautifully preserved. So this particular site's been so thoroughly excavated, but it's also a new type of analysis, this wear and tear analysis, essentially, that this team have used, where they've really scrutinised exactly what scratches and worn down erosion has happened to these flint tools, and they've sort of weighed them and measured them, and they've been able to date them very accurately as well. So they've seen how the smaller tools are earlier and these larger tools seem to come in at about this point in the early Stone Age. So we have this real kind of this revolution in chopping down trees, essentially. But what's really crucial about this is that it seems that sort of evolution of the change in human life and the change to more permanent settlements and to agriculture, that carried on throughout the Stone Age, and that was a change that sort of perpetuated throughout human culture.
Very surprising, because that's actually quite a long while after, for instance, people have found evidence of fish hooks, which are 20, 30,000 years old, and people building primitive boats. So they actually chopped down trees after they did those things, which is quite surprising.
Amazing. And I guess a sign of just being able to kind of have a look around you and see what resources are available to you, and then kind of modify your thinking and your inventiveness according to that.
Victoria, thank you. Well, from something that happened a very long time ago to something very much cutting edge and now, Dominic, what have you picked up for us?
Now, there's a curious material that we know is in our galaxy called dark matter. This is material that has mass but doesn't produce any visible light, which allows us to see it. And we know this material must be there because the galaxy is rotating faster than we can explain, just given the gravity of the stars inside the galaxy.
So its existence is sort of an inference at the moment. We can see how things behave. We know there's something with a lot of gravity there, but we just can't spot what it is. We know it's active, but we can't see it.
If it wasn't there, the problem is the galaxy would get pulled apart by its own centrifugal force. Something needs to be pulling all of this material in to keep it rotating. Now, in terms of the amount of dark matter inside a solar system like our own, we think it's not very much, because the galaxy is made up of very small solar systems with vast expanses of vacuum between them. And this dark matter is spread smoothly throughout the galaxy, and so there's far more dark matter between solar systems than there is inside any particular planetary system, which is perhaps only a few light days across compared to distances of light years between stars.
Oh, that's unusual. So the dark matter isn't all sort of aggregated in the centre or round the outside. It's spread right across the galaxy.
That's right. In order for material to collapse down to form a star, it needs to find a way of losing gravitational energy. And the way a star does that is by emitting light. The problem dark matter has is it doesn't produce any light, so it can't cool and collapse down structures. It stays in a diffuse distribution throughout the galaxy. But a paper published this week in the monthly notices of the Royal Astronomical Society by Silvia Garbari of the University of Zurich and her colleagues has actually measured the dark matter distribution in the vicinity of our own sun. And the way they've done that is to look at the way in which stars close to our own sun bob up and down in the plane of a disk. These stars aren't static exactly in the plane of a disk. They will tend to bob up and down with some characteristic frequency that you can measure. And by looking at how fast those stars are bobbing up and down, you can measure the force acting on those stars and see how much gravity is pulling those stars back towards the plane of the Milky Way.
And then we know the stuff we can see, therefore what the gravity of that is. So that must mean you can work out roughly how much dark matter that's gravitationally active that must be there too.
That's right. The way they've done this is to computationally model the motion of these stars with different amounts of dark matter added into their computational model. And then they see which model fits the observed oscillations of these stars. And they have found that in the vicinity of the sun, about 80% of the matter is visible stars like our own, but about 20% is dark matter.
So
Now,
our star has got dark matter in it.
that's why our own solar system has dark matter in it. And I did a quick calculation of how much dark matter this paper predicts there is within the orbit of the Earth, and it's 50 billion tonnes. So that sounds like quite a lot, but if you were to condense that into a rocky asteroid, that would be equivalent to the mass of an asteroid about 1.5 miles across.
So quite small, really. What is the implication of having demonstrated this, albeit with a mathematical model?
Now, there's an interesting question here as to whether dark matter in our own galaxy is spread in a spherical distribution or whether it's collapsed down into a disk like the disk of stars that we see. And up until now, people have thought that there's no mechanism by which dark matter would collapse from a spherical halo around the Milky Way down into a disk. But this is suggesting that there is a concentration of dark matter in the disk, so at least some collapse has occurred, so there is a concentration of dark matter in the disk of the Milky Way galaxy.
It's going to be quite hard to test that, though, isn't it? How are they actually going to take this forward? Because, again, it's just a theory at the moment, isn't it?
This paper was based on observations of 2,000 stars near to the Sun, and next year a mission is going to launch called Gaia, which will measure very precise distances and velocities of millions of stars close to the Sun. And once we've got that data set on the very accurate positions and velocities of those stars, we can model their motions with very high precision, and we will really start to understand what forces are acting on those stars.
Still won't explain what dark matter is, though, will it?
That's right. That's a question for the particle physicists to try and work out what this material might be.
From protons to photons and gluons to muons, The Naked Scientists. Science that's fundamentally more fun.
It's The Naked Scientists with Chris, Victoria and Dominic answering your science questions. We're going to Alex first. Hello, Alex.
Hi, Dr. Chris.
Okay, fire
Thank
away.
you for taking my question.
Go on, tell us about it. I'm dreading this I word, which is on the screen in front of me.
No, I actually enjoy ironing, and in fact, I was listening to your podcast when I was doing my ironing, which made me wonder if you could answer a question about it. I know that heat, pressure, and sometimes steam will take out wrinkles, and then if you use vinegar, which is a mild acid, it can help to set or remove creases from some fabrics, but not all. But I'm wondering, why does ironing actually work? Like, what happens to the fabric on to the fibers, to the molecules that makes it stay flat, and why in some fabrics when you iron a crease in, it stays there forever, usually like in a synthetic. But if you do the same thing in a cotton, you can iron it out again and it will return to flat.
I tend to buy those shirts that come pre-ironed and which naturally dry into that pre-ironed state because I'm quite allergic to ironing. You're obviously of a different persuasion.
Definitely. Although my husband liked wrinkles, he said they were more comfortable.
Oh, fair enough. How does it work? Well, thinking of the pure sort of physics of it, if you've got a very hot iron and you've got, say, a cotton, then the cotton is a polymer. And polymers are made of lots of long strands of molecules. And in order for molecules to get past or slip past one another, they've got to be vibrating. So if you look at rubber, for example, it's very stretchy when it's at room temperature, because if you make it warm or it's room temperature, then the molecules shaking around makes it very easy for them to slip past one another and to line up neatly. So your cotton is quite similar. If the iron puts some heat in and you steam iron, so you put some water in as well, then the water probably helps to dissolve some salts, which are from the washing powder and things, between the particles. It also provides lubrication, and the heat increases the energy of the molecules, so they're all shaking around, and this enables them all to slip past each other very beautifully and all line up and make a crease-free shirt. So I think that's basically the physics of why ironing works, because if you use a cold iron of exactly the same weight and even some steam or sort of water, it doesn't work in the same way. You need that temperature, don't you?
You do, yeah.
And, of course, you need the Naked Scientist podcast on in the background, as you have alluded to. Alex, thank you very much for your question. NakedScientist.com/podcast if you want to catch up with all of the back catalogue of this programme, going back about 10 years, actually, of programmes we've made. Dominic, there's a quick question here from Rabone Sissoko, who has emailed chris@thenakedscientist.com. It says, do cell phones affect the operations of aeroplanes? Why is it that some airlines allow you to use cell phones while you're airborne, others don't?
There are essentially three reasons which are cited for why people haven't been allowed to use phones on aircraft up until now. The first one is that there have been suggestions that the radio waves from the mobile phones can interfere with the operation of the aircraft. Secondly, it actually causes problems for the cell phone networks because phones work by finding out which transmitter mast is closest to the phone and then linking to that mast. Now, if you're up in the air, you can see an awful lot of masts and the network can't actually decide which mast to attach to. And the third problem is the social aspect of it being rather antisocial. You'd be shouting into your phone when you're in the air on an aeroplane.
People do that on my train all the time.
Yes.
Doesn't seem to bother them.
But of course, with the noise of the engines, you're going to have to shout quite loud to speak to somebody in an aeroplane. Now, in fact, the evidence that phones interfere with aircraft is very weak. There have been studies done, certainly by Boeing, to look at flying aircraft with and without phones on board. And there was some very weak evidence that planes with phones on board may have had slightly more incidents, but it was so weak it was probably just down to chance. So I think most airlines now don't believe that phones do interfere with aircraft. And you can get around the problem of having to decide which mast to attach to by having a transmitter actually on board the aeroplane, which uses the aeroplane's own communication systems to route your call to whatever network you're using.
Brilliant. Thank you, Dominic. I shall use my phone with impunity on the aeroplane and refer them to you if they tell me off. Now, this week, scientists have come up with a way to use pulses of electricity to stop certain forms of epileptic seizure. Yuri Bashaki from New York University led this work. It's published this week in the journal Science, and he's with us now. Hello, Yuri.
Hello.
First of all, what actually is happening when someone is having an epileptic seizure?
There are many kinds of epilepsies. The ones that we used as a model is associated with loss of consciousness. So you're driving in a car and you have an epileptic seizure and you lose complete control of your abilities to drive a car.
Okay, so if we were to record from the brain itself when these seizures are happening, what's going on electrically?
In this case, it's very easy to recognize because what happens is many neurons all of a sudden are enslaved into a common chorus. They just beat together and in very synchronous discharges, and these changes produce very large currents that can be measured even outside the skull.
And so once one little group of nerve cells is firing abnormally, this can then spill over onto other adjacent regions of the brain and propagate or reverberate around the brain, disrupting the normal function.
Exactly. Reverberation is very appropriate in this form of absence or generalized seizures because what happens is that there is a ping-pong mechanism between the thalamus and the neocortex. The thalamus sends out a synchronous discharge, enslaves neurons in the neocortex, which in turn send back a reinforcing pattern, and it goes on and on and on and on.
Until something breaks the cycle. So when people take anti-epileptic medication, what does that do to stop that happening normally?
Well, that's the reason why we did this study, is because in order to stop the seizures, you have to do something drastic, that you have to prevent that this pattern can occur. The magic drug would be, of course, is to have an impact only when these supersynchronous events occur.
So effectively, you've got to damp down the activity of the nerve cells to stop the seizure activity, but that's going to have consequences for people when they're not actually having a fit, isn't it? So an ideal situation would be to have a way of arresting the seizure when it's going to happen, but not having it on all the time, and that's really where your paper comes in, isn't it?
That's right. So we use an animal model. Luckily, this particular form of epilepsy has an excellent rodent model, and so we were able to record these epileptic patterns that occur hundreds and hundreds of times a day, so we could do many experiments. And it's not only that we detected these seizures, but we detected every single cycle of the seizure. And that's a critical point because the way you can break up a vicious cycle is interfere with it cycle by cycle. So, for example, a seizure is a rhythmic pattern. It's an oscillation, just like a swing. You can stop the swing by grabbing the person, and that requires a lot of energy, or just interfere with this swing cycle every single time when the person is up, for example. In this case, with very small amount of energy, you can achieve the same action, that eventually the rhythm, that is the swinging, will stop.
So you put a little bit of electricity into the brain when there are signs that a fit is about to happen?
So we used transcranial electrical stimulation, which are electrodes placed outside the skull, and applied currents at the time when we knew that the brain does not have neurons firing, that is, we can interfere with this reverberating self-sustaining patterns.
But do you only turn that signal on when the person is going to have a fit, or the animal in this case, so that you don't interfere with brain function normally?
So we applied the electrical stimulations only during the few seconds of episode when the seizures occurred, and never outside.
If you only switch this on when the animal's having the fit, does this appear to block the progression of that seizure, so do the animals spend less time fitting?
We have to wait until the seizure occurs, and this is when we start the stimulation. So our method doesn't prevent the occurrence of seizure, it shortens it.
And so if you were to translate this to a human, would it work?
I would be very surprised if it wouldn't, because the principles are exactly the same. There are a couple of technical challenges that have to be applied, because the signals that you can record from outside the human brain, we record it from inside the skull, are much smaller in the case of human. So the technical problems, the electronic problems are larger, but it's solvable.
Well, let's hope that you do manage to translate it soon. That was Yuri Bashaki. He is from New York University. He published that work this week in the journal Science. If you've ever turned on a tap for a glass of clear, cool water, and you've watched brown water coming out instead, clearly you've stayed at the Hammersmith Hospital in London, where I was a doctor. No, just kidding. You'll know that is less than appealing. And although it can be safe to drink, brown water is a problem in parts of Scotland, where there are largely private water supplies. Susan Waldron from the University of Glasgow is looking into why this is happening, and Planet Earth podcast presenter Sue Nelson went to meet her in the university's water and sediment lab to find out more.
The brown colour occurs when there is a high concentration of dissolved organic carbon in the sample, and the higher the concentration of dissolved organic carbon, the deeper the colour. And that dissolved organic carbon is coming from the soils that are in the catchment round about the drainage system. They break down and produce material that goes into solution, and then when we have movement of water from the catchment soils, such as under a rainfall event, we have movement of that carbon into the catchment water.
Now, you've got a couple of samples of water here, ranging in colour. Well, we've got a bottle of mineral water on the side there, so that's very clear. I suppose there's no way of putting this. There could be urine samples, I suppose.
Well, we like to think of them as closer to whiskey. But yes, the darker the colour, the higher the concentration generally of dissolved organic carbon. And in river systems, we can see concentrations that can be up to 60 milligrams per litre carbon, and they can really be quite dark brown samples.
Has there been an increase in the amount of carbon and the brown water that you get nowadays?
Within the UK, there are quite a large group of scientists who understand very well the processes by which carbon is transmitted into catchment drainage systems, and what they have observed is that there has been an increase in the amount of carbon that's going into water over Europe, the UK, parts of North America, and this has happened over quite a long time scale, about 20 or 30 years. There are multiple competing hypotheses for this, but the one that's most commonly accepted is that actually as we clean up our atmospheres and we reduce the amount of acid deposition that there is, it promotes the breakdown of organic material and produces this dissolved organic carbon that can then go into the river systems. So effectively, as the atmospheres become cleaner, the water can become browner. There are also...
That seems counterintuitive, doesn't it?
Yep, but sulfate deposition inhibited the production of dissolved organic carbon.
Sorry, what do you mean by that?
Sulfate deposition is your acid rain. Okay, so as we clean up the acid deposition that's coming from large-scale industrial manufacturing, we're cleaning up the atmosphere and we're not depositing so much sulfate on our soils, and we're increasing the amount of carbon that's being produced as dissolved organic carbon.
But water companies, I'm assuming, though, must spend extra money trying to make brown water clear.
That's correct, because aesthetically people don't like to drink brown water. It looks dirty. We associate the brown colour with soils, and therefore we think that our waters are contaminated with soils. And it could be that if the water is not purified of the material that gives it the colour, it may not also be purified of other components. So this is understandably why people don't want to drink coloured water. So therefore, the fact that our waters are becoming more coloured presents a problem for the water companies, because they have to invest more in cleaning up the water. And they need to also understand how the carbon is arriving at their water purification plants. So is it coming in at a continuous low level that's just increasing, or is it coming in spikes? And can their equipment actually cope with this increase in carbon concentration if it comes in a spike or not?
And what are you sort of discovering so far?
That land use change can affect the increase in carbon concentrations. We know well that there's a very strong hydrological response to movement of carbon into river systems, and that there's a seasonal component as well. So we understand that at the end of the summer, when we've had higher productivity in the landscapes and then subsequent breakdown of this organic matter, and we're supposedly into a wetter period when the catchments start to wet up again in the autumn time, when we have heavier rainfall, then that's when we have the largest amount of carbon moved into the catchment. But it's very interesting because we are potentially moving to a situation where we will have different levels of productivity as temperature regimes change. And as has been apparent over the past few months, where we've had the wettest quarter since records began recently, the time period when water is being delivered to the catchment also changes. So what we don't understand yet is how carbon will be delivered to the catchment under a changing climate. And that's very important, because the companies need to be able to understand better how to manage their resources and purify their water as best as possible. So we're taking our knowledge about what we know of the processes that generate carbon in the catchments, how it's delivered to the catchment, and then trying to understand how the changes might occur under projected climate change.
The University of Glasgow's Susan Waldron talking to Sue Nelson. And you can hear a longer version of that interview on the Planet Earth podcast. You can find that at nakedscientists.com/Planet Earth.
Bringing the facts to bear. The Naked Scientists.
This is The Naked Scientists. I'm Chris Smith, and also with me is Victoria Gill and Dominic Ford. It's our Science Q&A special. We're answering your questions. In a second, we'll be talking to Glyn, who wants to discuss the horrible R word that we've been overexposed to this summer, and that's rain. And also Kathleen in Lowestoft wants to talk about the question of wet hair, or what looks like wet hair. More rain-inspired questions. No, don't say the R word. Meanwhile, in the kitchen, Ben and Dave are doing our kitchen science experiment. How are you getting on? Have you electrocuted yourselves yet?
Luckily, there's been no electrocution here, at least none that we didn't intend. But we have used an entire bag of apples, and we're now into the oranges. And Dave, how much electricity are we actually getting from this circuit?
So what I've done is I've wired 7 sets of copper and zinc nails. So I've used nails instead of the 2p pieces because they're easier to wire up. And it's producing just below 7 volts of electricity. So that's how hard it's trying to push the electricity around the circuit.
Now that should be enough to charge your phone. You said earlier it charges from about 5 volts. So is that it? Are we done? Have we already got there and we've still got half an hour to go?
Well, we can give it a go, see what happens. I've mutilated one of my phone charging leads and wired the 2 sides of the battery onto it, and I'm just connecting it up now.
So now we can watch what happens when it connects. Now, the phone hasn't done anything at all. Oh, but the voltage has dropped enormously. It's gone down from 7 to sort of 3.5 volts, so something's definitely happening.
And I've actually also got it wired up to a meter which is showing the current which is flowing, which is about 93 microamps, so that's about a 10,000th of an amp. So tiny, tiny current. But the problem with these batteries is that they don't produce very much current. They produce a reasonable voltage, nearly a volt, but they can each only produce about 90 microamps of current. And to trigger the phone to make it actually charge, to charge your phone, you've got to probably get an amp for an hour flowing into it. So at the moment, this would take sort of 10,000 hours to charge up.
So what are we actually going to need to do to get it working in the next half hour?
Basically, I don't know if it's going to work, but I'm going to try wiring lots more of these together. So a few more one after another to get a higher voltage, and lots of them in parallel, so next to each other. So they're all helping each other to add to the current. So we'll probably have 5 or 6 of these all wired up together to try and increase the amount of current it produces and hopefully get over the limit which we need to charge my phone.
Well, this is certainly more than your 5 a day, but hopefully it will be enough to get that phone charged, and then we can make some calls after the show. So back to you, Chris.
Thank you. Thank you, Ben. It's keeping the supermarket in fruit sales, that one, isn't it? Glyn is with us from Cambridge. Hello, Glyn.
Yes, I'm here.
Fire away.
Rain falls from clouds, as we know. Thing that attracts it's gravity. So we get light rain and we get heavy rain. And the distance of the clouds above us is the same. Droplets will be slightly bigger and so on. But why do we get heavy rain that beats incessantly, bounces off the roads, or doesn't? Where does the energy come from that gives it that impetus and the energy that we feel down below?
Well, actually, it's interesting you've asked this question because if you're a regular Naked Scientist listener, you might remember we interviewed a gentleman earlier this year who had actually found fossilised raindrops. He had gone to South Africa and found some volcanic ash, and the volcanic ash had all these little dots in it, and he realised that these are fossilised raindrops, and he then went and got some Hawaiian volcanic ash and dropped droplets down a stairwell into this ash to work out what dot pattern he could get, and he was able to try and work out what the atmosphere of Earth would have been like when those rocks were fossilised millions of years ago, based on the impact pattern of the Hawaiian ash, extrapolating it back to the South African fossilised raindrops. And the assumption he was making in doing that work is that the raindrops are going to have a maximum size and therefore velocity in air, because as the air changes its density, so if the atmosphere was as dense in the past as it is today, then you would expect the raindrops' maximum velocity and size and so on all to be the same. So it's quite an interesting way of going about the study. But basically, when you have a rain cloud, you've got lots of little nucleation sites. These are sites which will allow a droplet to form from the vapour in the cloud. And those droplets will attract water to them, and they will reach a certain size. They will be held up in the cloud by updrafts, so air rushing upwards. And the stronger the updraft, the bigger the particles that it can support in the cloud before it lets them drop down. So if you have a fairly weak updraft, then the particles are not going to get very large before their attraction down to the Earth's surface under the force or attraction of gravity is going to overwhelm the updraft and they'll fall. But if you have some very strong updrafts, which in big storm clouds can be really strong, they will support fairly bulky droplets for quite a long time before the droplets get really very large and then they come cannoning down. Thank you very much for the question, though. Great one. Kathleen's on the way with her question from Lowestoft. Vic.
We just have a question that's come in on Facebook from Pekka Oilinki. She asks, given the exciting news that we've had recently about the Higgs boson, almost certainly, pretty much definitely found, can we now think that light needs a medium in order to transfer, just as sound needs air in order to transfer? So, Dominic, do you have any thoughts on that?
Now, this has to do with two theories of physics called quantum mechanics and special relativity. And the question that was troubling physicists about 100 years ago was whether light is a particle or a wave. And the problem is you can describe some properties of light as being extreme particles and some properties such as diffraction and refraction in terms of a wave-like motion. And what physicists decided was that, in fact, it's both at the same time. So light is made up of particles that we call photons, but it's also made up of waves of electric and magnetic fields, which are electromagnetic waves. Now, the question is, do those waves move through some medium, like ripples on the top of a pond, or do they just move through the vacuum of space? Now, if they are like ripples in a pond, then if you travel at some speed with respect to that medium, then you should see light travelling at different speeds. And experiments have determined that light travels at the speed of light, however fast you're travelling in whatever direction. And so that suggests there is no medium through which light travels.
While you're there, Vic, this is I like this question. I've got to ask you this because Kenny Kang wants to know what's more contagious, a cough or a sneeze. What do you think?
Interesting question, actually. So this will all be connected with how far the particles that you sneeze or cough out travel. So it would be interesting to sort of take a measurement on your average cough and your average sneeze. So, I mean, they're both very similar processes, but they come from irritation in different parts of the respiratory system. So a sneeze is the irritation of of your nasal mucosa, of the skin in your nose, and that causes a sort of expulsion of air to basically protect your airway. If there's something irritating there, then you want to get rid of it. Your body reflexes to get rid of it. Similar with a cough, but that comes from sort of the airways inside, so that's your lungs expelling that air. I would say probably a sneeze, because that's a more sort of explosive expulsion generally, but it would also depend on what disease particles are carried and whether they're airborne, because if you're talking about something like tuberculosis, which is an airborne viral particle, then that's extremely contagious, and whether you're coughing or sneezing, you wouldn't want to be anywhere near that.
Dave, we subjected you to something similar, didn't we? Made you sneeze by inhaling pepper to see how fast it went. How fast was your sneeze?
Yeah, I had a very exciting afternoon inhaling pepper outside the back of an ice skating rink in the middle of Cambridge. It was behind the police station as well, but no one picked me up for it.
Sniffing this strange powder and then sneezing.
I think I was quite lucky. It was very unpleasant. It certainly came out over 100 miles an hour when I filmed it with a high-speed camera and measured it. It was a thoroughly unpleasant experience.
But it was all in the name of science, Dave. That's what's important. You can actually watch the footage, can't you? You've got that on the Naked Scientist website, if people want to see you sneezing.
Yes, if you look at the nakedscientist.com/kitchen science, somewhere in amongst those there is a very unpleasant picture of me sneezing.
Thank you, Dave. We'll leave you to get on with stuffing wires into fruit. We'll come back to you in a second and find out how you're getting on. Meanwhile, Kathleen is in Lowestoft. And meanwhile, if you'd like to join us, by the way, email chris@thenakedscientist.com. Hello, Kathleen.
Hello, good afternoon. Right, I've got a friend and her hair is absolutely amazes me. I keep getting the hair dryer. I will dry her hair bone dry within 15 minutes. All the perspiration will be pouring down her forehead, pouring down the back of her neck. Her clothes get wet. And I don't understand. I asked my doctor, why is her hair, winter and summer, always soaking wet? She perspires from the head. And he said he didn't know. And could I ask you?
Wow. So do any other bits of her become excessively sweaty? Or is it just her hair?
No, just normal everywhere else. But for some reason, she perspires on her hair all the time. I've been out with her last year when it was snowing, and I said to her, do me a favour, just take off your hat for a few minutes and start to tice up. And I just don't understand why.
No, it's a bit of a mystery, but it's a very interesting question, Kathleen. I can only think this is a sort of manifestation of a condition called hyperhidrosis. Hyper meaning a lot of, hydrosis meaning water or sweat. Now, normally this affects the hands. People often say they get very excessively sweaty hands, and this is actually a recognised medical condition, and it can be treated. And one way in which it's treated is to interrupt the nerve supply that controls sweat glands in the skin in the neck. There's something called the sympathetic chain, which is a nerve pathway which carries sympathetic nerves that drive sweating up the body, and they go out from the top of the neck down the arms. And if doctors go in and make a tiny lesion in the sympathetic chain there, it can stop the sweating of the hands. I haven't heard it happening in the head, though. And there are other reasons why people sometimes do sweat excessively. So it might be worth our while getting things checked out just in case, and having some various check-up tests done just to make sure that nothing's being missed. Dominic, David Spence, who is listening in the Shetland Islands in Lerwick, he says, what's the temperature inside a black hole? I must admit, I never really thought about it.
It's actually incredibly hot. At least the surface of the black hole is very hot, because as material is falling in towards the black hole, it's being compressed into an ever smaller volume of space. There's less space close to the black hole than there is far away from it. And so that material is elevated to tremendous pressures and tremendous temperatures of hundreds of millions of degrees, which means it doesn't just glow red hot, it glows hot in ultraviolet and X-ray light. And that is how we can detect that black holes are there, because we can detect this very hot material producing X-rays with X-ray telescopes. Once it's actually past the event horizon, it's very difficult for us to say what happens to that material beyond that point, because we can't see it and we don't fully understand what laws of physics apply inside the black hole itself.
Terrific, thank you. Well, let's come back to Earth for a second. Can you help, Vic, Molly with her jam making? What she says by her email, chris@thenakedscientist.com, is, I make jam at home, and the recipes I use are always very specific about the amount of sugar and fruit to be combined with the pectin. While attempting to make jam a few weeks ago, I was short half a cup of fruit, but I went for it anyway. Unfortunately, it never set, and it's more of a peach sauce than a jam. Oh dear, why is that?
Not enough pectin, really. I mean, it depends on what fruit you're using. Different fruits have different amounts of pectin in them, and the whole chemistry of jam making is all about sort of making this pectin that's in the fruit break down and become water soluble, and then that recombines in all of those hydrogen bonds that are holding it together recombine in a chemical reaction with the fruit acid and with the sugar, and that makes a lovely network that forms a gel, and that's the kind of jelly-like substance of jam. So you need to get that chemical reaction right to get the pectin amount right, the fruit acid right, and the amount of sugar right, so that you make the right consistency of that network that will hold your gel together, your jam together, so you don't get fruit sauce.
What does the pectin do that enables that to happen?
The pectin's actually sort of the backbone of this structure, so that it holds together. It's a long chain carbohydrate, basically. So it's a polysaccharide. So it's this long kind of interlinked connected chain that's held together by hydrogen bonds. So it gives the fruit its rigidity, and it will give your jam that gel-like sort of semi-rigidity. But you need to break it down so that it's not too stiff. If you have too much pectin, then it will recombine in this really, really kind of quite solid, sticky, thick form. So you have too much pectin. And if you don't have enough of it, or you haven't boiled it for long enough, or you haven't sort of got that balance right to achieve that chemical reaction where you've got this flimsy enough kind of structure within your gel that's basically a lattice structure that it forms within your gel that will hold your jam together nicely. So you can, it sounds like she's using commercial pectin as well, and sort of having that extra cheat which you can use, but you do need to get those amounts quite right. And there are other cheats you can use, like you can reboil it up and throw in a bit more fruit acid, so you can kind of cheat the system to just get a little bit more of that chemical reaction going, so you can fix it.
Right, let's get back to the kitchen and find out how the boys are doing with their fruit-powered battery. Are you about to phone us up and prove this works?
Oh, I wish we could. We've got chains and chains of nails here, but it looks like actually getting enough voltage and enough current out of this system is going to take quite a lot more than we have in 1 hour. But Dave, how are we doing?
Well, at the moment, everything has fallen apart and it's all dropping on the floor.
So this is the problem with using fruit instead of using real batteries. You get fruit juice everywhere, everything goes slippery. It's really not a safe electrical situation.
Yes, and it turns out that wiring up enough in half an hour is quite challenging.
So what could we do? What would we need to do to make it better and to make sure we could charge?
So essentially, I think you need at least 5 times as many wires as we had beforehand, all wired up in parallel. At the moment, I've got halfway there. I've put all of the zinc nails in, but I haven't got enough of the copper ones in, so I can't really test it.
So the electrochemistry is sound. We know it would work if we just had that little bit longer. So we're going to keep going now and hopefully get Dave's phone to charge. So that's all we have, Chris. I'm sorry we couldn't quite do it for you, but we'll call you in maybe an hour.
Brilliant. Thank you very much for trying anyway, Ben and Dave. Right, we're slightly running out of time, so we're going to try and sneak in very quickly this question. I understand that Mark wants to talk about Saturn. Hello, Mark.
Hi, how are you?
Very well, thank you. What would you like to know?
We know that planets form around stars when all the leftover gas and dust clumps together to form them. I would like to know why all the material that makes up the rings of Saturn doesn't do the same thing. It seems logical that it would come together to form one or more moons, but that's not what we see. In fact, all this material appears to be uniformly smooth without any clumping whatsoever.
Now, the problem is that the material is so close to Saturn that it feels a very strong tidal force. Now, the moon, we know, induces tides in the Earth's oceans, but similarly, the Earth also induces tides in the rock of the moon. And that would also happen for a body orbiting Saturn. And the closer that body is to Saturn, the stronger those tides are. And those rings are really quite close into a very large gas giant planet. And so they feel incredibly strong tides. And that means that anything that tried to clump together where those rings are would immediately be pulled apart by those tidal forces.
Oh, I get it. So basically, there are some little moonlets, but basically it's really hard for them to exist because they're just going to get ripped to pieces. But what about the moons that do exist? Because, say, Jupiter has got some very large moons around it, so has Saturn. They're not being pulled apart. So how did they get stable in the first place then?
Now, this, I should say, is not well understood, and people are researching this at the moment. I think the current thinking is that those moons must have formed further out in Saturn's system, and then they must have migrated in as a result of exchanging energy with other moons.
Because they stretch and bend quite a bit, don't they? I mean, if you look at some of the moons of Saturn, say Enceladus, for example, squirts out material into space because it's being stretched and deformed as it goes around in the gravity field.
That's right. I mean, you can have moons where a tidal force is so strong that they effectively have anti-gravity. So the tidal force is stronger than the gravity which is pulling the moon together, like Phobos and Deimos orbiting Mars.
Dominic, thank you very much. Right, well, from one very hard question to another, it's our question of the week, and Hannah Critchlow has been soaking up the summer sun this week to help us with this particular question.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
This week we ask if human skin behaves a bit like a photosynthesizing plant.
This is David from the States. Is it true that we get vitamin D from the sun? And if so, does that mean that we, like plants, photosynthesize?
We first call on vitamin D expert Dr. Laura Tripcevich from Surrey University.
We need vitamin D to maintain our bones and to make sure we absorb enough calcium from our diet. One of the main sources to humans, radiation from the sun, can penetrate the layers of the skin called the epidermis, where there's a chemical called 7-dehydrocholesterol. And this absorbs the UV light and then will produce a pre-vitamin D molecule. And then, because the skin is quite warm, this pre-vitamin D3 will spontaneously convert to vitamin D3. And the vitamin D3 will move from the skin and will be pushed out into the capillary system and into your blood system so that it can then be activated and used.
So, human skin does make vitamin D using a photochemical reaction. How similar is this process to the photosynthesis occurring in the chloroplasts of plants, which uses the sun's rays to convert carbon dioxide into oxygen and carbohydrate?
My name is Richard Cogdell, and I'm the Hooker Professor of Botany at Glasgow University. In vitamin D production, the wavelength of light which triggers that reaction or drives that reaction is the ultraviolet wavelength. So the wavelengths that actually would burn you if you were out in the sun for too long. The wavelengths of light which drive photosynthesis are the wavelengths that give rise to the blue and red regions in the spectrum because it's light absorbed by chlorophyll. And so photosynthesis is not driven by ultraviolet light, it's driven by visible radiation in the blue and the red regions of the spectrum.
So what happens during the winter months when the intensity of all wavelengths of sunlight hitting the UK decreases? Plants enter a dormancy phase and use remaining carbohydrates stored up during the summer months. But what happens to us humans? Back to Laura.
You can only make vitamin D3 here in the UK between the months of April and September. You can be out in the sun for about 10 to 15 minutes 3 times a week, just your arms and face. You don't need to strip off. And this should see you through into early autumn. We now know that the half-life of vitamin D can be around a month. Now, there are dietary sources of vitamin D that can support your levels during the winter time, and they would be things like oily fish, like sardines and mackerel. There's a little bit in eggs. If you like, shiitake mushrooms are in there. And there's also little bits added into breakfast cereals and milks and soy milks and things, but you need to check the label to see if they are actually in there.
Thank you, Dr. Laura Tripcevich and Professor Richard Cogdell. Evan A.U. and Lou Jane, that's me, agree, adding on the forum that sunblock does reduce the level of ultraviolet light reaching your skin. So it's a trade-off between decreasing the incidence of skin cancer and increasing the incidence of vitamin D deficiency. They also think that this question of the week conjures up visions of green-skinned humans. We next open our ears to crunch a data question just downloaded from the Naked Scientist inbox.
Hi, I'm Dan from Malvern. I have a telephone line coming into the house, 2 twisted wires, as everybody else does around here. How is it possible for a telephone conversation, a download to 1 or 2 computers, and someone else listening to a program and maybe even watching BBC News? How does that all happen at the same time? Be interested to know the answer to that.
Send us your thoughts. You can tweet at Naked Scientists, write on our Facebook page, email Chris at The Naked Scientists, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. That's it for this week. Thank you very much for joining us, and thank you also to our guests, to Dominic Ford and to Victoria Gill for lending their knowledge to the programme, and also to our production team, Ben Valsler, Dave Ansell, Mira Senthilingam and Martha Henriques. Our next programme will be in 2 weeks' time because we're taking a bit of a break, and it will be all about the nervous system. And after that, we're back properly at the beginning of September with a show looking at internet security. So if you have any questions or thoughts or comments about how to keep the World Wide Web safe, then send them in now. It's chris@thenakedscientist.com. Goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.